In this video, we will do Excel project 10 for Unit 10 of our Statistics OER course on the goodness of fit test, the chi-square distribution. Make sure you open the PDF description to follow along and you download the Excel file to work on it. So according to this project description, we will submit an Excel file with our answers. We will use Excel to recreate the technology needed to find the test statistic for a chi-square goodness of fit test. A study indicates that the number of televisions that American families have is distributed as shown, and this is the given distribution for the American population, and it is on the table on the left, and a random sample of 600 families in the far western United States resulted in the data shown in the table on the right. So if we read carefully the table on the left, we have a column for the number of TVs, and then we have a column for a percent. So even though these numbers are whole numbers, they are percentages, and when written as values, they have to be decimals or percentages. And then on the other table on the right, we have the number of TVs and the frequency that this particular number of TVs occurred when within a sample of 600 families in the far western United States. So we will perform a goodness of fit test to see whether the far western United States number of TVs per household distribution follows the American distribution. We want to embed formulas in Excel to complete the process as shown in Art of Stat. We want to perform a hypothesis test at the 1% significance level using the p-value, and then we want to perform the same test using a critical value. So in Art of Stat, we want to use the app chi-square test, goodness of fit test, to perform the test. And that is all the way at the bottom of the online apps in Art of Stat, inference for comparing several groups, and we will choose the chi-square test. And when we are in chi-squared, we don't want to be in the tab that says test for independency, homogeneity. Instead, we want to be in the goodness of fit. So when you are in the goodness of fit test, let me see if I can move this so I can read my project while I'm doing it. Okay, so when I'm here, it says select the contingency table for the choice to enter data, change the number of categories to 5, and replace the default category labels with the ones from the problem. So here I'm going to select the contingency table. I'm going to change the number of categories to 5. And here I'm going to click in these boxes, and instead of category 1, I will write 0. And category 2, I will write 1. And these are the number of TVs. And category 3, I'm going to write 2. And category 4, I'm going to write 3. And for category 5, I'm going to write 4 plus. And then in the counts, I will have to enter the counts from the sample. So they have to be the 66, the 119, the 340. So 66, 119, 340, and then 60, and then 15. And then here I have to do the probabilities. Now remember that these must be decimals, whereas your project is giving them to you in percent form. So the 10% is 0.10, the 16% is 0.16, the 55% is 0.55, the 11% is 0.11, and the 8% is 0.08. And you want to submit. So let me make this smaller. Take a screenshot of your entries and paste it in the Excel file started at cell J2. And I'm going to do that, and you should do it after pausing the video. So I did that while I had paused the recording, and now I have the screen in ArtofStat posted here. And the continuation of this project says that we want to embed formulas in Excel that complete the process shown in ArtofStat. The only difference is that we will enter data in columns instead of rows. So we want to use variable locations in our formulas instead of actual numbers. And the first step would be to enter the observed values from the table above in B8. And then in B3 to B7. And then in B8 to use the sum function in Excel to add the observed values and obtain the size of a sample, which we hope is 600. So observed frequencies, I'm going to copy them. 66, 119, 340 if I remember, 60 and 15. And here equals sum, and I'm gonna add the values above, and that was 600. And in C3 to C7, I want to enter the expected percent values from the problem in column C, and then in C8 add them and hope to get 100% or 1. So these proportions here, you can enter them as percentages. If you want, you can say 10%. Or if you want, you can do whatever you did in ArtofStat, which was decimals. So it's up to you, whichever one you think is best. 0.16. I'm entering them as decimals. 0.11 and 0.08. And I'm going to copy, and they come out to 1. After that, in D3 to D7, we want to insert a formula with variable locations to calculate the expected values of a sample for the same size. The size of the sample is found in B8, and for this reason, if we want to reference the location in B8, we would like to use the dollar signs so that when we paste as we move along the spreadsheet, that location always stays the same. So make sure that the entries in this column agree with the entries in ArtofStat in the row expected counts. So when I was here in ArtofStat in expected counts, I see that the values are 60, 96, 330, 66, and 48. And I want to make sure that after I do my math agrees with this math, assuming that ArtofStat is correct. So the expected number will be equal to the proportion for this category of 0 TVs times the total. And the total is in this location 600. And I would like this to be with dollar signs so that when I copy the formula only changes the proportion value. It doesn't change the location of the total. And you can see here that I found the same ones that ArtofStat found, and if I copy the sum formula, it will indeed add to 600. So the next step is to calculate observed minus expected, and observed minus expected equals my entries in B, that's the observed, minus the calculations in D. That was the expected, and I'm gonna find those, copy and paste my formula, and hopefully when I add them up, the answer will be 0. So we want to now square this. So in column F, I'm going to take the calculation of column E and square it. And then in F8, calculate the sum. And in B12, explain why F8 is not 0 anymore. Actually, I forgot in the previous step to say in B11 state the value of the sum of the residuals. So in B11, what is the sum of the residuals? It was 0, which is what I would be expecting to find if I would just add the differences between the observed and expected. So let's find this sum again. I'm going to copy and paste the sum formula. Why is it not 0 anymore? And now it is 1790. The answer is, why is this not 0? It is the sum of squares, and squares are positive. The next part is to fill in column G, G3 to G7, insert the formula for the Pearson residual. It will be the square of the differences that we calculated in column F, divided by the expected value that we calculated in column D. So this will equal to the square to the left of that cell divided by the expected number that we calculated in column D. And I'm going to copy this. And in G9 and H9, I'm going too fast. In G8 and H8, I want to enter the sum of all the calculated values in cell G8. So here I'm going to say equals the sum of the Pearson residuals that are right above me. And I want to make sure this entry equals the entry in ArtofStat test statistic chi-squared, and enter this title in cell H8. So let's double check that this is what we found here. If you see here, test statistic chi-squared is 29.65, and my answer is indeed all rounds to 29.65. So this will be test statistic chi-squared. Chi is another Greek letter, so insert symbol, and I want to do the chi over here between phi and psi, and chi-squared. There we go. For some reason, after I enter a Greek symbol, it just enlarges the font. I don't know why it does that, but I can fix it just by changing the font size to be the traditional 11 point. Okay, let's go to the next one. G9 and H9. In G9, insert the formula to calculate the degrees of freedom for this distribution. You want to use the count function to find the number of categories in our test. Enter a title in cell H9. So in our test, we have 5 categories. We actually had to enter that number in ArtofStat before we even started to generate the contingency table. But the count function in Excel does not count text. It can only count values, numerical values, and the entry 4 plus is actually text. So what you want to do is you want to count the observed frequencies instead, and that will give you the size of your sample. Now, in goodness of fit test, the degrees of freedom equals the number of categories minus 1. So here my degrees of freedom, I'm going to call them df, will equal to the count of the observed frequencies which will hopefully will be 5, minus 1. So you want to make sure you subtract 1 over here. And that is indeed 4, as expected. And again, I can double check with ArtofStat. ArtofStat did indeed say here that the degrees of freedom were 4. In cell G10, use the function chi-squared distribution dot right tail with the test statistic and the degrees of freedom you found above to calculate the p-value. So I'm going to do that. So this will be p-value. Not there, so let's try again, p-value. And here I'm going to use the chi-squared distribution, that right tail right here. It says what is your x, that's your test statistic, comma, where are your degrees of freedom, they are right above it, and close this, and it will give me this p-value that is 5.77644 times 10 to the negative 6. So 10 to the negative 6 means that this 5 is located 6 places after the decimal point. So the number, the correct value in decimal form would be 0.00000. That will be 5 zeros, 577,644. So here I see that it tells me that the p-value is less than 0.0001. And I also see here that when it rounds it to a percentage, a tenth of a percentage is again 0.0. So it looks like my answers are correct, as expected. At the 1% significance level, does it appear that the distribution number of televisions of far western United States families is different from the distribution for all the American population as a whole? In B15, enter the null hypothesis. So the null hypothesis is that the distribution of the number of televisions of far western United States families is the same with the distribution for the American population as a whole. And the alternative hypothesis in B16 will be that the distribution of the number of televisions for far western United States families is different from the distribution of the American population as a whole. In cell B18, I'm supposed to enter the decision with mathematical explanation. So the p-value indicates a very unusual result coming from the theoretical distribution that assumes that the far western United States have the same distribution of TVs in their household like the whole United States. So my decision here would be to reject the null hypothesis because the p-value is less than alpha. And my conclusion would be that at the 1% significance level, the sample data provide sufficient evidence to support the alternative hypothesis. Make sure you write the alternative hypothesis as you wrote it in B16 to support the claim that the distribution of the number of TVs in far western United States families is different from the distribution of TVs of the all American families as a whole. Remember to always start at the 1% significance level and keep going to write your conclusion. In G11, I want to enter the significance level as a decimal, and in H11, I want to enter the title of this value. So the significance level for this hypothesis test was 0.01, and that was the significance level, or alpha. And in G12, we want to use the function chi-squared dot inverse dot right tail to find the critical value for the hypothesis test above. use the variable locations for alpha and degrees of freedom from earlier. So here I want to find the critical value, that's the title. So critical value. Critical value is the chi-squared score that gives you the 1% significance level, borderline, because remember that you are calculating the area on the right side of the curve. So the function is again chi-squared inverse dot right tail. So select the correct function. It says, what do you want the probability to be? I want it to be 0.01, comma, and what do you want the degrees of freedom to be? I want the degrees of freedom to come from my calculation in G9. And I'm going to close that. And it says, well, the critical value is 13.276. So in B23, we want to explain mathematically how the test statistic and the critical value can be used to support the decision entered in B18. And the idea here is that if we are in the chi-squared distribution, right here, and we go in find percentile quantile, and we have a distribution that has 4 degrees of freedom, and we are looking for the percentile in the upper tail to be 1%. Then we will have found this critical value of 13.277 if rounded to the nearest thousandth. That said, that from this value on and to the right, so larger chi-squared scores will be in the unusual 1% of the population. This is called the critical region. So the critical region of the 1% unusual results would be values or test statistic values, chi-square scores greater than 13.277. And the chi-square test statistic that we found was 29.65. And that was greater than 13.277 and therefore in the critical region. So therefore, since the test statistic is in the critical region, we have sufficient evidence to support the alternative hypothesis, and we will reject the null hypothesis. So here you want to write something of the form, the test statistic, so the chi-square test statistic is in the critical region, which means it is greater than the critical value of 13.277. And therefore, we reject the null hypothesis. And you can rewrite your conclusion if you want, or you can summarize it. But the critical value explanation is that my test statistic was in the critical region, which is greater than 13.277.